Thank you for the invitation. I went for beers with Kyung-Yun last night, and I'm kind of worried about what I said was going to be in my talk because he was like promising a lot of stuff I'd talk about. I was like, uh-oh, I don't remember saying that. If you go look at the proceedings of ACL, which is one of the main natural language processing conferences, or EMNLP, which is another one, a few years back, you would have seen when Word2Vec was hip and everyone was using it, a bunch of papers in the semantics track on a new way of doing word embedding, so a topic that I personally find really dull. And now, if you look at this year and some of last year, LSTMs or recurrent nets or attention or deep learning just generically are in many, many titles. And I think it's fair to say that we've reached a point where using RNNs or variants on RNNs to model sequences, to model sequence-to-sequence mappings, and to learn representations of units of text, of whole sequences in order to label them or classify or perform interesting and exotic tasks has become one of the dominant paradigms. So in terms of like applications of deep learning to natural language processing, I was thinking, what could I talk about? You could just go to the proceedings of these conferences and read a dozen great ideas from each conference and just draw inspiration for your own research from that. Obviously, in the previous lectures this week, we've covered a lot of the maths behind RNNs, some sequence-to-sequence modeling, and some memory. So I thought, OK, I'm not going to revisit that. So I thought to myself, what could I write for this summer school that would be interesting for people here? And I thought, what would I like to have at this stage in my research when I'm starting my PhD or about to start a PhD or in the early stages of a PhD, or even something I'd like to hear now, which is what sort of intuitions guide the selection of a particular model for a particular problem? What sort of intuitions drive us to improve or extend models and decide how we're going to improve and extend them? And I'm not going to answer that question because that's the open question of research. But I'm going to try and give you some insight into my opinions on the matter, my intuitions about the matter. A lot of stuff I'm going to say might be controversial or intentionally just a little sort of a high level, so don't take it all at face value, take it with a grain of salt, but hopefully it will be interesting. So I'm going to talk a bit about, that's not a good start. So today I'm going to talk a bit about the limitations of RNNs for standard sequence modeling and sequence-to-sequence mapping, how some of these limitations have been addressed by augmenting them with various forms of memory. So there will be some topical overlap with what Sumit talked about the other day. I wasn't actually at that lecture, so I'm hoping the content overlap won't be too high. And I'll try and use this to illustrate what sort of, at least what my thinking process in designing or analyzing models is, and hopefully that will be somewhat informative when you're working on adapting existing models like RNNs, LSTMs, attention to your own problems and thinking about how to fix, extend, improve these models. So I'm going to there'll be 6 parts. I'm going to sort of take a break 1/3 of the way through and 2/3 of the way through. These are fairly bite-sized, so I'm hoping I'll get through all this in the time allotted. I'm going to start by talking about transduction bottleneck and sequence-to-sequence mapping. So this will be in relation to the idea of having an encoder and a decoder, nothing fancy, no attention, why that works in spite of the model. Moving on from that, I'm going to try and talk about the limitations of recurrent neural networks at a slightly higher level. And this will be not so much mathematical and more on the sort of intuitive side. On the basis of that, I'm going to revisit the notion of a recurrent network not as a specific kind of cell or specific set of functions, but more as an API for putting a subnetwork structure into. And I'll talk about how attention, stack-enhanced RNNs, and register machines like neural Turing machines fit that API and what's interesting about them with regard to the original limitations. So the transduction bottleneck, I'm going to go quickly through the sort of like background section since this is the nth time you've heard of the definition of an RNN. Chris Dyer pointed out that the RNN diagram sort of looks like a little standing man, so I added a little hat. This is the only joke in the lecture, I promise. I was just so proud that I made it look so, OK. So recurrent neural network cells are going to output the distribution over a variety of things, like the next symbol in a sequence, a label, or in some cases, we're not going to actually care about the output. And they connect back into themselves. And the idea here is that this hidden layer that connects back into itself by looping preserves state and then can therefore model the history of a sequence or long-range dependencies within a sequence. RNNs are very popular for language for obvious reasons, because you can unroll them across a sequence to to basically form a sort of feed-forward network. They dynamically adapt to variable length sequences. We have a lot of those in language. We have no way of controlling how long a sentence will be in our data set. How many sentences they're going to be in a dialogue, how many sentences they're going to be in a paragraph or document. So it's nice to have this nice adaptive capacity. They're very popular because recent research has shown that they can capture fairly long-range dependencies, as Kyung-Yen talked about earlier today. They have obvious applications in natural language processing, and again, Kyung-Yen talked about quite a few of these earlier, so I'm not going to dwell on these too much, but we can do language modeling, so we can use the chain rule for probabilities to infer the probability of the sequence according to a corpus, the statistics of a corpus. We can do sequence labeling for online, so we start reading in symbol by symbol, and for each symbol we output a particular label, for example, if you're doing speech to text. We can do sentence classification, so we can unroll an RNN across a sequence and then either take the final state or do some new mean pooling, so averaging across all the outputs in order to get a single representation of that sentence and then classify into sentiment, classify into topic if you want. But for a lot of these approaches, there are simpler or better models that exist, both in traditional statistical sequence modeling and in neural networks. This may be a little controversial because we've had a lot of recent advances across the last 2 years. But I still think that constrained language models are cool. I still think that log bilinear models are cool. So there are sometimes better, simpler solutions. What makes RNNs really cool is that this idea of state being able to capture dependencies within the history of the sequence extends to being able to capture dependencies outside of the history of the sequence. Or to put it another way, we can condition the output sequence on arbitrary vector representations. So, for example, instead of just if we ignore that red vector and what's on the right would be simply unrolling an RNN across the sequence to do, say, language modeling. If we initialize the start state or feed in an arbitrary vector at each input, we can skew the distribution of strings that's going to be output by the model towards something conditioned on arbitrary data, such as a string from another language, such as a vector representation of the topic of a document, or anything you want. So in this respect, I agree fully with Cho that being able to model the likelihood of a sequence, the conditional likelihood of a sequence, is kind of a fundamental part of a natural language understanding. This idea of being able to condition the generation based on arbitrary representations that you might have obtained from another part of your network has led to this idea of doing sequence-to-sequence mapping with recurrent neural networks. Many natural language processing and other tasks are, in fact, castable as sequence-to-sequence transduction problems. Cho famously in several lectures has boldly claimed everything really boils down to translation, and this is kind of my version of that outrageous claim. But translation obviously is an example of English to French transduction, for example. Parsing can be seen as taking a string and then transforming it into a tree. And if you really want to drink the Kool-Aid, computation itself could be seen as taking input data and mapping that sequence of data into the result of the computation. And we'll see some examples of that. More formally, the goal of sequence-to-sequence mapping is to transform a vectorial representation of some source sequence, which might have a different length than your target sequence, and we want to map that into into the target sequence. How this is typically done with RNNs is we're going to represent the source sequence as a single vector, and then model the conditional distribution over the next target token with recurrent neural networks. So we read in the source in the most naive form, we read in the source sequence, produce the vector representation by taking, let's say, the final hidden layer. Then we train a separate RNN, or maybe an RNN with similar parameters, to maximize the likelihood of the target sequence given that conditioning vector. And at test time, we can generate the target. We feed in the source vector, and then we can generate the target sequence greedily, or use beam search, or a variety of methods to get better output. Another way that this has been presented is as an encoder-decoder model. So you can think of this is mostly what I've talked about there. Sorry. So what are an example of how this works for translation, which again overlaps with Cho, so I won't talk about this too much, is you're going to have an RNN that reads in the words of your French sentence, and maybe you can stack the RNN in order to capture dependencies better or have a more expressive model. Reads in the French words token by token until you reach a delimiting symbol or an end of sequence symbol. And at that point, it's going to start outputting the words of the English translation. At training time, we're going to feed in the correct output as the next input. At test time, we're going to take the argmax or sample from the distribution over words here and feed that in. And that's been quite successful, as Ilya Sutskever showed. In fact, I'm going to argue that it's successful despite the architecture of this model. Another cool application, again, so we're again talking just about simple sequence-to-sequence mapping models with RNNs, was this paper by Wojciech Zaremba and Ilya Sutskever in 2014, where they read simple Python scripts character by character, and then would output the numerical result of computing that Python script character by character into a full stop. And this, when it came out, blew everyone's minds. And it is a cool paper. I mean, it's a cool result. But I mean, you obviously have to look into what the data is a bit more carefully. They're short Python scripts. It's actually a very, very restricted subset of Python. For loops are never nested, and in fact, always have this kind of formulation of iterating over a particular range and then incrementing or multiplying a particular variable. So they're, in functional programming parlance, closer to a fold or a reduce. But it was very cool that this worked at all. In fact, in 2014, I was like, we've solved AI. So that sounds really cool. So can we solve machine translation with this? Can we solve computation? Well, impressive results notwithstanding, there is an architectural defect in the simple sequence-to-sequence mapping model with LSTMs, which I like to call transduction bottleneck. So if you look at what's happening in this simple case of translation, you're going to ignore the output of the encoder RNN until you reach some separator symbol, and then you're going to start decoding into English. Then when you're training the model, you're going to get gradient with regard to the log likelihood or negative log likelihood of the correct token. That's going to go back into the network and flow back. This bottleneck goes two ways. So you can think of, when you're decoding, all the information required to produce the English sentence, all the information from the French sentence, needs to be in the hidden representation at this state. This is a fixed size hidden representation, so it means that, guess what? If you have longer and longer sequences on the encoding end, and you have a fixed size, then you're going to have to compress more and more, and you're going to expect increasingly lossy decompression when you're decoding. But it's really the effect on the backward pass, which is the bottleneck. All gradient that the encoder, and in fact these representations are going to get, has to flow via this single point. On the decoder end, you're going to happily get gradient flowing through two sources, one through the forward history, and two through the actual predictions. Whereas here, it has to just go through possibly crushing tan H's, or if you have something like a GRU or a LSTM, through a bunch of gates. And it's reasonable to expect that to still be an imperfect transmission of gradient back to the encoder. What this means in practice is when you're training a machine translation model, again, without attention, without any sort of fancy stuff, the majority of the training is dominated by learning the target sequence language model. So if you take your model when it's 80% trained, because you know how long it's going to train for, and you sample like what sort of strings are going to come out of it, you'll find that it's typically going to be ignoring the encoder altogether. And it's only towards the later stages of training, when gradient has started to propagate to the encoder, that the right sort of behavior of conditional generation of the English given the French is going to happen. So I think this is fairly intuitive, and again, if you disagree, we can talk about this later. But I think it's fairly obvious that while it's a cool model, it's translating in spite of the architectural constraints. So we're kind of fighting against a bottleneck that shouldn't be there. So that's sort of the empirical sort of intuitive explanation of a problem with this very simple approach to sequence-to-sequence modeling with RNNs. But I'd like to talk about the limitations of RNNs from a more computational perspective. So who here has taken a class on like theoretical computer science? OK, a few of you. Good, good. Is this completely foreign to anyone? This kind of hierarchy? Okay, I'll give a very quick explanation. So in theoretical computer science, we have a hierarchy of automata of like theoretical computing mechanisms that can perform different sort of degrees of complexity of computation. Or in formal language theory, which has nothing to do or little to do with actual natural language, there's an equivalence between automata and classes of languages. So for example, finite state machines, where you simply have sort of a set of states and a transition matrix between states based on the symbols that you're reading in a string. That's equivalent to the class of regular languages. These are languages that can be recognized by regular expression. If you take a step up and you add a stack to your finite state machine, you have a pushdown automata. And that actually allows you to recognize a larger class of formal languages, context-free grammars. Context-free languages such as those generated by context-free grammars. And we typically think that actual natural languages are formal languages of this or higher. And then skipping up a bit, at the top of the computational hierarchy are Turing machines, which are the sort of one of the fundamental models of modern computation. And their equivalence class is recursively enumerable languages, or in mathematical parlance, all the computable functions or primitive recursive functions of arithmetic. So those are super powerful, and we want like these are computers. These are sort of like slightly more crippled computers. Quick show of hands. Where do you think RNNs are on this kind of hierarchy in terms of what they can be trained to do? Who thinks finite state machines? Okay, one. Who thinks pushdown automata? Okay, and who thinks Turing machines? Okay, great. Okay, there's a bit of no hands up here. You guys have, or is this an ill-formed question?
If you have enough precision, they can do Turing machines.
Okay, so in terms of what RNNs can express, there's this paper by Siegelman and Sontag in 1995 that shows that RNNs can express Turing machines. The hopefully vaguely correct sketch of this proof, since I haven't read this paper in 5 years. In fact, this might not be exactly their proof. But any Turing machine that's basically a set of states, a finite set of states, a finite language for the tape. And does anyone not know what a Turing machine is? Do I need to explain a Turing machine? It's a controller, and it has an infinite tape, and you can move over the tape and write symbols and read symbols. And conditioning on what symbol you are, you transition states. So a set of states, a set of symbols that can be written to the tape or present on the tape, and a transition function which reads the symbol that's currently at the read head on the tape and decides what action to perform, which might be outputting another symbol or shifting left and right along the tape. And it's fairly obvious that you can translate this deterministically into an RNN, which will do the same thing. So you take one hot encoding of the hidden layer, one hot encoding of states are going to be the contents of your hidden layer, which will have size q. You have one hot encoding of your symbols as input, so that the tape is external to the RNN. You have one hot encoding of symbols and left and right as outputs, and identity as a recurrence, and then finally your transition function as an update matrix. And you can, therefore, for any Turing machine, map it into an RNN by extension. Most RNNs will be able to express at least a set of Turing machines. It might not be a very interesting set of Turing machines, but you can, if everything goes to something one hot and you have appropriate output functions, you can say, look, there's a Turing machine that can be expressed here. When you learn about neural networks, you hear the function approximation theorem, and everyone thinks, hooray, we're going to solve everything with a neural network. And obviously, it's cool that you can approximate any function with a deep multi-layer perceptron. That doesn't mean you're going to be able to learn that function. And likewise here, expressivity is definitely different than learnability. So just because an RNN can express a class of Turing machines doesn't mean you should expect it to learn those Turing machines. And in fact, I think it would be absurd to expect that. And there's a few reasons why. Simple RNNs, and this includes GRUs and LSTMs, and by simple I don't mean trivially simple because there are some of the authors of these models here, but I mean ones not extended with some form of external memory or attention. I think they cannot learn Turing machines through normal sequence-based maximum likelihood training. The first reason is that RNNs do not control the tape. So typically, the training, when you're training these models, you unroll the RNN across the sequence. Yes?
I disagree because it is the tape. The memory, the state is the tape.
You could simulate, but then it would be fun. It'd be fun.
Think about neural Turing machines. The memory is just part of the big recurrent net.
Yeah, I mean, so formally a Turing machine would still need an infinite tape, but okay, I'll take your point. I'll get to whether or not neural Turing machines are Turing machines a bit later in this talk. I'm not going to prove any of these things. So like, take this with a grain of salt. But if you think of the tape as being outside the RNN, then we don't control the tape sequences. The sequence has to be exposed in a forced order during the training. And so the ability of the model to output left-right doesn't actually affect what you're going to be exposed to. Now, obviously, this is why I say with that little asterisk, during normal sequence-based training, you could look into using reinforcement learning to actually control how the RNN is exposed to the environment, which would be the text, but I won't go into that now. Even if you think about other ways in which it could simulate the tape internally in its hidden layer, the fact that we train them with a maximum likelihood objective, so that we want to maximize the likelihood of the data or the labels given the input conditioned on some parameters. This produces models that are close to the training data distribution. So they haven't. Yes?
I was just going to ask if you can clarify, when you say they can't learn them, do you mean that because of the maximum likelihood objective they can't, or because you need additional assumption, for example, on how the data is collected?
No, I think
assumptions that would allow this, which I guess Yasha's comment would suggest that there are a set of assumptions under which you can. It's just maybe you're not willing to make these assumptions in practice.
Yeah, so I'd have to think about that a bit more, but yeah, I think like definitely the way we typically collect data and expose data to the RNN doesn't fit the assumptions that I think you'd want in the sketch of that earlier proof. I don't know if that.
I guess I would suggest, I don't think there's like a typical way in which we collect data.
Yes.
Right?
Yes.
And so you mean if the data is collected under a fixed policy that is not necessarily the one that you wish to evaluate?
Oh, sorry, I misunderstood your question. So you're suggesting that sometimes the data that we present to an RNN with regard to, let's say, classifying won't actually induce a Turing machine just because of the set of examples we present to it?
I guess I'm suggesting more broadly, there are cases, assumptions under which data is collected in which we may be able to learn, and there's other assumptions under which we may not.
Okay. Yeah, I think I'd have to think about this further. So this isn't particularly meant to be an authoritative proof. This is kind of my hand-wavy argument against the proposition that RNNs are going to learn Turing machines. So I think that when using a maximum likelihood objective is going to produce a model that's very close to the training data distribution. So they're bad at generalizing to out-of-sample data, despite they do it better than some other models, but they're not going to generalize to the extent of learning a general computation mechanism. We want to encourage models to sort of fight against the maximum likelihood objective and generalize by introducing forms of regularization, such as dropout, such as putting an L2 norm on the weights, or an L1 norm, which encourages weights to be sparse, which would actually bring us closer to what we want for encoding a Turing machine in an RNN. But I still think it's insane to expect simple regularization mechanisms like that to just dump out a Turing machine in your model weights magically. Now, feel free to prove me wrong, but I think it's good to have like reasonable expectations about what your model is going to learn and disregard magic. Yes?
So I feel like there's the asymptotic case if you have infinite data, infinite computation to train and optimize, and you should be able to learn any kind of Turing machine, supposing the network is big enough to hold the computation. But then, of course, in practice, we want to learn with a finite amount of data and finite computation. And so all of these architectural tricks or constraints that we're putting in could work well when the kinds of Turing machine things we use in computer science are appropriate. So this is what has happened in the last couple of years, and more will come. But it's more like an encouragement to find solutions that fit this computational model.
Yeah. So the fact that we have limited data, not sort of and we don't provide infinite data to our models means that they're going to find an adequate enough solution. So I'm going to argue, and this is again this is an opinion, definitely on the realm of opinion, that RNNs, in practice, are just going to learn to approximate, albeit fairly large, but finite state machines. This is simply because in a lot of problems I've tried to train, a RNN, LSTM GRU baselines to do something as simple as copying large sequences. There's absolutely terrible out-of-sample performance in that you can learn to copy sequences that it's never seen before, as long as the length of those sequences is within the bounds of what it's seen during training. And as soon as you make them a little longer, it starts to forget. So empirically, I've formed this strong belief that RNNs, LSTMs, and GRUs are just going to approximate large finite state machines with a finite n. So they're effectively modeling order n Markov chain. But unlike n-gram models, say, you don't need to specify n in advance. So they're very flexible in that if you get some larger data that has longer range dependencies, it's going to be able to extend that n and adapt. So if indeed you bite the bullet and buy that RNNs are approximating large finite state machines, this means that they're, in theory, memoryless. But in finite state machines, you can simulate memory through dependencies. So for example, if you take a regex, like dot star a dot 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 a, which means ignore a bunch of characters, and then if at the end of the string I see a followed by 3 symbols, we don't care which ones, and another a, then recognize. You can translate this into an actual sort of generative model over the last character if you feed in the string until you need to predict that last character, and then that will induce a distribution over whether or not the final character should be a, given that I've seen a 4 symbols ago, which should be 1 in this case. So you can capture this very limited, bounded form of memory through these dependencies, even in finite state machines. And that's what I think we've been seeing in these simple sequence-to-sequence models that allows them to translate. But there's no incentive under the maximum likelihood objectives that we train sequence models and sequence-to-sequence models with simple RNNs to learn dependencies beyond the sort and range observed during training. And so
I disagree with that statement in the sense that a lot of times, especially for recurrent networks, you have a sort of inductive bias that forms that may be able to learn larger dependencies than what you're training in the sense that, yeah, sure, it can potentially learn just those dependencies in the range you are examining, but that would mean for the RNN to ignore its sort of periodic or even the properties it has as a dynamic system, in the sense that, imagine, for example, you have a very simple model that's only able to learn rotations, right? What you're saying is, yeah, of course, you can potentially learn something up to 1 times it or 2 times it or 3 times it, but if you're learning a rotation, you keep composing that rotation, you will learn some periodicity, which is an arbitrary long dependency.
yeah, but typically you'll find even those models, their ability to keep the period going and output ABC, 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 it might degrade with time. So you're always getting a bit of noise in the process. It's never, I think, unless you hardwire it, it's never perfect.
I agree with that, but still, never.
I take your point that it could, for some constraint. This is obviously this is A, not a proof, and B, we're talking about in the general case. I think that in most cases you'll have difficulty learning longer range dependencies than those observed during training.
Sorry, one last comment about
Yeah.
what you said. So what you're saying is, yes, it's true that the system might still be chaotic, and it's probably because it's very nonlinear, and eventually an epsilon of change will degrade over time, but still that doesn't mean that the time needs to be constrained by the range of your examples. It could still, even if it's finite, it could still be way, way beyond your range of training.
Okay, I agree with that to a certain extent, but I also think that there's still going to be a limit that's driven by the training examples, after which you're going to find a sharp drop in degradation of performance. But again, I'm sure that there are corner cases where we can happily train RNNs on fairly synthetic data where they will generalize beyond that. I'm just saying in most cases, you will find a pretty severe drop in performance when you extend the length of the sequences, but there's nice generalization within the bounds of that length, which is why I say they're approximating large finite state machines. So what's wrong with RNNs approximating large finite state machines? Well, there's a few issues, both architectural and non-architectural. The first is that the RNN state is acting both as the controller, so determining what state it's in, but also as the memory saying, okay, this is like the history of, this is my complex state, right? This is what I've seen so far. the longer the range of the dependencies you want to store in the RNN or recognize with the RNN, the more memory you're going to require, so the larger your representation is going to be. This should be fairly trivial. Tracking more dependencies also requires more memory. So yes, we've shown in like machine reading, I'll give you some examples that you can track very long range dependencies, but one, with an RNN happily. But if you're doing something like copying even fairly short sequences where each symbol has a dependency from the input has a dependency to a point in the output, as you would expect in machine translation, then you need larger and larger representations the more of these dependencies you're tracking. If you have more complex or more structured dependencies, so you want to output C because you've seen A and B within a particular local dependency with each other, you're going to need more memory. And finally, finite state machines are pretty basic from a computational perspective, so maybe we can do better. Let's bring this back to language for a second. A natural language, as I said earlier, is arguably, if you ask linguists, depending on which linguist you ask, at least context-free, which means we need something at least as expressive as a push-down automata to model the syntax and arguably the semantics of language successfully across all human languages. I don't actually believe this proposition, but I'm not going to argue that point today. I'm going to say simply that even if it's not, so even if natural language, so English, is a regular language in formal language parlance, rule parsimony matters quite a lot for the tractability of your learning problem, for your the ability of your model to learn a set of rules. So here's an example of what I mean by that. Let's take the smallest, well, at least one of the simplest context-free languages that will not be recognized by a finite state machine, which is A and Bn. So it's the set of all strings where you have a number of A's and then the same number of B's. If in practice n is bounded by some capital N, so there's only a finite set of strings, then this becomes a regular language again. The regex that recognizes that regular language is actually fairly complex. It's going to be empty string, AB, or AABB, or AABBB, up until NAs and NBs. So you're going to have n plus 1 rules there. A context-free grammar that will recognize that entire set of strings and then obviously up to the infinite case just has 2 rules. So if you're saying, OK, in practice it's bounded and I don't care if I can recognize longer ones, you still have a nice incentive for using a context-free grammar because you only need to write down 2 rules, versus a regular language where you have to write down a large number of them if n is large. So if you think about what your model is expressing, what its actual, practically speaking, expressive capabilities are, what would you pick for a problem that is describable as, if you have the choice between one that can solve your problem but is going to need to basically internalize n plus 1 rules in its weights, and one that internalizes 2 rules, which one do you think is going to be easier to train? It's obviously the one on the right. So even if your problem is regular, it's worth looking into slightly more expressive models. So just to sort of summarize this point, I'm arguing here, and again, this is an opinion, so if you strongly disagree, then you might be completely right. But I'm arguing that we're kind of here with simple RNNs, LSTMs, and GRUs at the level of finite state machines. A lot of interesting problems in computation and natural language understanding probably require us to be somewhere up here. If we want to simulate a computer with a neural network, as is the dream of the neural Turing machine authors, we arguably want to be up here. So how do we get there? We've had quite a few questions, so if you just, in the sake of time, we can skip to the next session unless someone has extra questions at this point. OK, perfect. So I'm going to talk about how we can at least try to take a step up in the computational hierarchy by augmenting RNNs with various forms of memories. And again, you'll have had concrete examples of this in Sumit's lecture yesterday. I'm going to not talk too much about specific models and more about the sort of generic principles behind different forms of memory, and leave it to you to read the papers or invent your own within this kind of framework. So I want to revisit RNNs. We typically have seen RNNs, LSTM, GRUs as this kind of beast where you have some sort of hidden representation, it loops back onto itself, you feed in vectors and you pop out vectors which might model distributions. And that's definitely a recurrent neural network. But perhaps influenced by the development of libraries like Torch, Theano, and TensorFlow, I've come to try and think, at least convince myself, that RNNs are more like a generic kind of API rather than a specific kind of cell. So we can fit several things inside this generic box. But the API is that it's going to be expecting inputs and outputs, and it's going to have a previous state and a next state. So in the case of a simple RNN, you have your inputs and outputs, and you have your previous and next state. But we're going to talk a bit in the rest of this lecture about what else you can put, sort of more structured representations in here, and how that's going to help with having a more expressive model. LSTMs you could also see as like fitting into. So there's a bunch of, this is purposefully complex, but there's a bunch of different wirings that you put to get the gates to work. But at the end of the day, they still fit this generic API that you get inputs and outputs. Previous state and next state are now pairs of vectors, so it's a slightly more complex API. Mathematically, we're going to be talking just generically as this RNN cell as a function which maps things from an input domain paired with a previous state domain and produces an output, some elements of an output domain and a next state domain. The elements of these states can be vectors, they can be tensors, they can be scalars, they can be nested or grouped sets of scalars, and we're going to see a lot of examples about when they're not just simple representations. Also, typically, you're going to find that in most applications that the previous state domain and the next state domain, these are types, obviously, are going to be the same. So you want your recurrence to always produce the same class of vectors. But I'm going to show you at least one example of where that constraint isn't necessarily met and everything's fine. Also, in a lot of cases like language modeling, your input domain and your output domain are going to be the same. And you might have some non-differentiable function that maps your outputs back into your inputs, like taking the argmax of a distribution over symbols. This API needs to satisfy a few constraints, at least, and there are a few exceptions for this. But basically, we want the gradient with regard to the next state, the gradient of the next state with regard to the inputs, the gradient of the next state with regard to the previous state, the gradient of the output with regard to the inputs, and with regard to the previous state, all to be well-defined. So we want those partial derivatives to be existing. So to just summarize briefly where I'm going with this whole idea of like stepping up into the API, stepping out away from individual cells into this generic API. We want this. We're introducing this kind of framework where you want to basically just keep everything differentiable. Use your previous and next, your P inputs and your N outputs to track state. Within the cell, you can do whatever you want, and we're going to see some very structured sort of functions for this. Because these you can sort of like see these as modules, so you can nest them, you can stack them. That's quite nice. And I'm going to show you in the next few slides how we can address some of the issues discussed before in this talk with this API by separating within the cell the controller, so whatever is responsible for tracking state and making decisions about what to do with input and output, from the memory, which is going to contain some information pertaining to the history of the sequence or the containing elements, or the conditioning elements. Illustrating this within this kind of box-like framework is we're now going to have a controller, which might be an RNN or an LSTM or a GRU, deal with the input and output. And we're going to have some interaction with the memory. And the form of this interaction is going to be the main difference between attention, NTMs, and stacks. And then the previous state is now going to be pairs or triples or n-tuples that we unpack into the memory and the controller hidden states, and then we repack them into the next state. So let's start with an illustration of how attention, or read-only memory in computational parlance, fits this API. And you've had an introduction to attention in one of the previous lectures, right? Yes, in Suma's? Okay, so this will be revisiting some of the things you've seen, but generically attention you can think as read-only memory. So you have an array of vectors that represents some data. You have a controller, so that's your memory. You have a controller that deals with the input-output logic. And you want your controller to be able to read your data array at each time step and consume that data in some form by either using it to update its own internal representation or influence the output of the controller. And finally, you want to be able to accumulate gradients in your memory. So you want the way in which you interact with this array of vectors to be differentiable in order to pass information back in the form of gradients to the source of those vectors, so an encoder, for example. How this fits into this API is there are various ways. The sort of early fusion, is Cho here? Did you come up with the term early fusion?
Yes.
Oh, yeah, cool. OK, I like this term. So there are various ways in which you can sort of like hook up your memory, your read-only memory to your controller within this API. The first simple approach, which is kind of the idea that your controller is going to be conditioned, the updates on your controller state are going to be conditioned not just on the inputs in its previous state, but also on some read from the memory. And then from that, the controller will decide what the output is. This kind of, we're not going to have a lot of maths in this lecture, but this is as far as I'm going to go. It's very underspecified mathematics. But the early fusion approach is going to have a previous state, which is going to be the previous state of the controller, and some fixed memory, which is independent of the time step you're at. The controller, which might be an LSTM, is going to take in some inputs and its previous state, update its representation, and produce an output. The next state is simply going to be the next state of the controller and the memory unchanged. And the inputs in the early fusion case are going to be concatenating the actual overall inputs to the model, to the recurrent cell, sorry, with some read from the memory, which will be a function of the previous state of the model and the memory. So in the early fusion case, the state of the model at the previous time step is sort of looking ahead saying, I'm going to need this information from the memory at the next time step fed into my input. A typical way of modeling attention is to simply take the matrix vector product of, you want to first compute a distribution over the rows of the matrix. So you're going to do that by taking your hidden layer and perhaps transforming it with a linear transform, multiplying that by the matrix. You can put a tan H or a sigmoid there if you want. You softmax over that to get a distribution over the rows or columns of the matrix, depending on if you're doing row major or column major. And by multiplying this distribution by the matrix, you simply take the expectation of the rows of the values of the rows of the matrix according to that distribution. So you're going to get a single vector out of that. Another option is to do late fusion. So whereas early fusion was saying, I'm using the memory to update my internal state, late fusion is saying, OK, it's like, and my internal state's going to tell me what to look for in the memory, and I'm going to use that to influence or the content of the output vector of the controller. So how this works mathematically is we're going to have the same sort of notion for the previous state and the next state. We're going to update those with the controller. The controller output isn't going to directly serve as the overall output of the overall cell, but instead we're going to use that to and the hidden state of the controller in order to look at the memory, get a vector out of it, and then compose those through addition or take the mean or take whatever sort of differentiable function of two vectors that you want, and use that as the overall output. So how does this fit in with the encoder-decoder sort of schema that we've been discussing earlier? Well, here the encoder is what's going to be responsible for producing the array of representations that will serve as a memory. So for example, for a variable width sequence, so the source language, a string of French, for example, you're going to have one vector per token. That's going to be a representation of the sequence at that position. You're going to pack those into an attention matrix. And the decoder is going to be a perhaps separately parametrized RNN and plus memory model in our framework with the attention matrix produced by the encoder as the memory. So now, because we're accumulating during decoding gradients of the error with regard to the memory, we can then simply just pass those back to the encoder, and those serve as gradients of the error with regard to the encoder. So this is nice. Now the encoder is no longer gradient starved. It's getting gradients not just through the connection to the decoder if you want to pass the final state of the encoder as start state for the decoder, but it has all the gradients coming through the memory. This allows us to compute soft alignments between sequences, as Cho discussed, and that's nice from a linguistic perspective because alignments do exist in sequence-to-sequence data, in particular in translation, and be able to infer those from the data is a powerful augmentation to your model. We can also use attention to search for information in larger sequences, and I'll give an example of that. And finally, memory on the forward pass isn't touched, so once you've produced your memory matrix, you don't have to update it during the forward pass during decoding. So you can just have that. It might seem quite expensive in this kind of schema to pass a big block of vectors through all time steps. But this could just be a pointer to a particular matrix. I don't know how easy that is to implement in TensorFlow. Is Jeff Dean here? But in Torch, this was super easy to do. So it's nice and it's efficient. And this allows us to directly address this problem that we discussed in the very first part of this talk with this bottleneck. So no longer do we need to just pass gradients through this single vector all the way back into the encoder. But if you're doing attention at each time step, you can see that information flows forward through the recurrent state, but also through these very thin arrows I've added here to sort of indicate attention. And that means that gradient is no longer just flowing back through the through the decoder states back into the encoder, but also at each point, you're actually getting the same benefits in a sense as the decoder was getting. You're getting a gradient with regard to the output of the encoder at each time step. So that is like one of the reasons I think attention has been so successful and such a nice general versatile model. So Cho talked a bit about the application of attention to translation. I just want to illustrate this with a few examples outside of machine translation that are very similar, that fit sometimes a sequence-to-sequence modeling, sometimes not. Textual entailment is one of the applications where we found that RNNs with attention have yielded great empirical improvements over other methods. If you're not familiar with this task, recognizing textual entailment is you get a pair of sentences, and you need to say whether or not there's a contradiction between these sentences, whether there's no connection, or whether there's an entailment relation. And in the simplest case, you don't have to specify the nature of the contradiction or the direction of the entailment. So for example, if your hypothesis is a man is crowd surfing at a concert, that contradicts the man is at a football game. That is no relation to the man is drunk, although that's plausible. Sorry, there was another crap joke. And finally, that entails the man is at a concert. So you need to be able to read two sentences and classify into three classes. Tim Rocktashel, who is an intern at DeepMind last year, adapted a word-by-word attention mechanism very similar to the one Yoshua's lab used for machine translation. But here we're not using it for sequence-to-sequence mapping. We're reading in a pair of sequences, and we're only just classifying based on the final state. So all you care about is this final representation, and then you have a multi-layer perceptron, which classifies into entailment, contradiction, or no relation. But the attention here is serving a very similar role as in machine translation. It's allowing you to provide alignments between the hypothesis and the premise on a word-by-word basis. And we can visualize these alignments using similar sort of heat map that you've seen in the machine translation alignment cases. Which find interesting connections. So for example, the hypothesis had kids, and the premise had a young girl and a young boy. And even though they're discontiguous, it found that, look, there's a discontiguous alignment between these two things that matches the entities being mentioned in the premise. And I thought this was really cool. Now, you always have to take these sort of visualizations with a grain of salt, and that is like you can cherry pick them. And we tried not to, but we had a bias to produce nice ones. In the paper, we did show examples of failure. And it's far too easy to read too much into like the expression, like seeing the face of your favorite deity in burnt toast. So always take these with a grain of salt, but I found it very convincing, that at least very encouraging, that we could capture these sort of structured dependencies with attention rather than straight through the RNN layer. I talked about using attention not just as a method for computing alignments, but for searching a possibly very large bit of text. Condition on like a question, a small bit of text. We produced last year, or about a year and a half ago, a large-scale supervised reading comprehension data set where you'd read a news article, and then you get a closed-form question where you need to predict what the missing word here was. And we had an anonymization strategy which prevented simple degenerate language modeling solutions. So in fact, you wouldn't see Oysen Timon or Friday or Clarkson, but you'd see random strings that were entity markers. But this was quite exciting, and we had a simple attention model which we trained over this to produce representations. The encoder would read the text and produce representations of each position in the text. The decoder would read a smaller bit of text, so it was an encoder-decoder kind of model. So the decoder would read another small bit of text, which was the question, and then classify into the answer. And again, we can see heat maps of a different sort. We can sort of visualize the strength of the attention over the text conditioned on a particular query. and we see that it does pay attention to a few likely hypotheses, but focuses on the correct one. And this example was nice because answering this question required some degree of anaphora resolution. See that things like he referred to the sailor in the text. So that was quite cool. Again, maybe there's a little bit of cherry picking here, who knows, but it's cool to see that there are examples like this where you find complex dependencies in the text. So attention is to quickly summarize, successfully mitigates some of the limitations of the original sequence-to-sequence modeling. So obviously it's being used in every other paper these days where you're wanting to do sequence-to-sequence modeling, but I hope this provides some intuition as to why, what limitations it's overcoming. It's versatile and adaptable to many problems that fit the sequence-to-sequence paradigm, and in fact just sentence classification paradigm, as we've seen in textual entailment. It can be tailored to specific sorts of processes, so you can have kind of esoteric or slightly structured forms of attention like pointer networks, which instead of producing the expectation of the vectors according to the attention variable, actually produce a distribution over those which your network uses directly as the output. And they're helpful for learning a good source of representations because by propagating gradients back to the encoder, you're forcing the encoder to learn good representations of each position in the text. But these are very strongly tied to the task at hand, so maybe they're not the sort of generic sort of language representations we'd like to be learning. On the other hand, this read-only kind of model puts a strong onus on the controller during decoding to track what's been read. So if you're doing iterative attention, because you're not changing anything in the attention matrix, the controller needs to learn the logic of saying, okay, if I'm trying to capture the fact that I've read this, and then I've linked this fact to that fact, and I've linked that fact to this fact, and now I'm drawing a conclusion, it needs to remember that it's read fact 1, fact 2, and fact 3. So that does put a lot of pressure on the controller that it would be nice to alleviate. Read-only also means that the encoder needs to do a lot of the legwork. Fortunately, it's getting a lot more gradient than in the standard sequence-to-sequence setup, but it still needs to learn good sort of index vectors for the decoder to search over. And that may also be a limitation of this type of model. So we're 2/3 of the way through. Are there any questions about what I've talked there, or was there so much overlap with what Sumit talked about yesterday that there are no questions? Good. Okay, cool. So this brings us, we're doing well with time. So briefly in the last part of this talk, I'm going to talk about taking we've talked about so far how attention overcomes this sort of transduction bottleneck I talked in the first part of this talk. And to finish, I want to talk a bit about overcoming the limitations I've hopefully vaguely successfully argued for, although I completely understand why there are dissenting views in the room. That RNNs are approximating finite state machines, and we'd like them to be a bit more expressive. I know that Sumit didn't actually get around to talking about stacks yesterday, so hopefully this will be completely new. So we want to take a step up in the hierarchy from finite state machine to pushdown automata, which means that, okay, if our RNN is modeling a finite state machine and a finite state machine plus a stack is a pushdown automata, let's just add a stack and bring us up to this level. This is going to bring us back to this general schema of the controller memory factorization. This is going to provide a slight difference with attention where interaction was one way, insofar as the information was coming from here to here based on keys or search vectors being produced by the controller. Now the controller is going to not just read from the memory, but also write to it in a structured way as you would with a classical stack. This interaction is going to basically take this sort of form and illustrate it slightly differently. You're going to have an RNN cell that reads the input from your document and produces output over labels or the next symbol, or during decoding is going to read in the previously generated symbol and then produce a distribution over the next symbol. And at each time step, it's going to write to the stack by pushing vectors onto it or popping vectors off. And it's going to obtain at the next time step a read from the head of the stack. The stack itself fits the RNN API, so this is a case of like nesting RNNs, except one of the RNNs has no parameters, and it's just arithmetic updates forward and backwards. But at each time step, it's going to be expecting an input, which is going to be a push signal, a pop signal, which are scalars, and a value vector, which is what the vector being pushed onto the stack is going to be. And it's going to have a state, which is going to be separated into a value matrix, which is all the vectors stored on the stack, and a strength matrix, which is how much each of those vectors is at that time step still on the stack. So there's a weird sort of disconnect between the mathematical implementation of the stack, which is going to have all the vectors ever pushed onto the stack on it, And then that combined with the strength is going to produce the logical stack, which is actually allowing you to say this is what's actually currently on the stack. This is the actual state. The output is simply going to be a read of the head, so it's going to be a vector with the same dimensions as the values stored on it, and there are no free parameters. How you hook this up into, this is quite what I liked with starting to think about this RNN API as being something you can put a lot of structure into it. You can start to think about this as wiring up these diagrams like I did in school with electricity. It was very cool. So the way this fits into this overall API of input, previous state, next state, output is that the input from the previous state is going to be the previous read from the stack, which is going to be concatenated with the input. It's going to be the previous hidden layer of your RNN controller. I used an LSTM. And it's going to be the actual previous state of the stack, which will be patched into the stack. The RNN is going to, based on the previous read and the input at a particular time step, output the overall output of the network, so a prediction over the symbols. It's also going to output the inputs to the neural stack, so a vector to put onto it and push and pop signals. And then based on that, the arithmetic updates in the neural stack are going to produce deterministically the next read and the next state, which will be concatenated with the hidden layer of the RNN to produce your next state. So it's fairly complex sort of wiring, but this is just, and this is not the only way you could wire these two things together, and in fact, this is not the only way you could model a stack. But this serves to illustrate how inside this fairly simple API, which previously we used to model a single LSTM, a single RNN, or a GRU, you can put in very complex arbitrary structure, and as long as everything's differentiable, you can unroll this across time and be happy. Yes?
Come to think of it, you shouldn't even, or I mean, you could get an even more powerful model by instead of just pushing data onto the neural stack, you would have a separate stack for the weights matrices of the RNN.
Yeah, so you can push what vectors you put onto that this is, as I said, first, this is only one way to implement. I'll illustrate a bit how the stack works in a second, but I'll list also other stack-based approaches. So there's more than one way to model stack. There's more than one way to formalize the interaction between the stack and the controller. So if you wanted to model some sort of recursive computational state, so actually model this as a computational stack in the von Neumann architecture style, you could push at each time step the entire RNN state onto this, and then instead of just concatenating it here, like have a gating mechanism and do super fancy kind of stuff.
I'm not seeing the RNN state, I'm seeing
Or the weights. Oh yeah, you could do that too. I mean, yes, because you could do that differentiably.
it could essentially reprogram itself, run closure.
Yes. Yes, you should be creative with these things. That's definitely a valid way to do this. This is an overly complex diagram to show that you can put incredibly complex structure within this API and get sort of slightly more complex computational behavior. And it's up to you how to design it, as long as you satisfy the constraints that you get differentiable pathways between the outputs and the states. Just to quickly illustrate, because I've been talking about a stack without explaining how we can actually make a stack differentiable. It's a classically discrete data structure. We're going to simulate a discrete stack, or at least approximate a discrete stack, by allowing the push and pop signals, which are typically discrete operations in the classical stack, to be continuous values between 0 and 1. And I'll give you an illustration about this. I'll talk briefly about about Julien Mikolov's approach in a few minutes as well. So at a particular time step, the controller, let's say, wants to push a vector v with a push strength, d for down, of 0.8. So you can interpret this, it's not really probabilistic, but you can interpret this as how certain the controller thinks that that vector needs to be pushed to the top of the stack. So we're simply going to add that vector to a matrix of zeros. So there will be a matrix and a vector of scalars here. Or we're going to logically put this vector onto the stack and associate with it a strength scalar, which is simply going to be the push signal. When we read from the stack, we're going to read from the top of the stack down up until a cumulative strength of 1, right? So here you have a vector v that has a strength of 0.8. That's all that's on the stack. So my read vector is simply going to be that vector scaled by its associated strength. So if you think here about discrete push and pop, where that's either a 0 or 1, if I pushed it with 0, there'd be a strength of 0, so then my read would be an empty stack. even though this is mathematically on the stack but not logically so. And if it was a 1, my read would be the most recently pushed vector onto the stack. The ability to have continuous values here makes everything differentiable, but I talk a bit about discretization in a second. At the next time step, we want to pop a bit. So the controller says, OK, I want to pop with certainty 0.1. And after that, I'm going to push. You want to pop before pushing if you want to do these things simultaneously, because otherwise you're destroying information you just pushed onto the stack. So I want to pop with strength 0.1. And so popping just removes, just by simple subtraction, strength from the head of the stack. So we take what the previous head of the stack was, and we remove that popping energy down to 0.7, following which I'm going to push a second vector with a strength signal of 0.5. So now we have this stack of incompletely pushed vectors, in a sense, because I popped a bit off the previous one, and I've pushed in a part of a vector. And I'm going to read down to a cumulative strength of 1 again. So I'm going to read v2 scaled by 0.5. And to that, I'm going to add v1 scaled by 0.5 rather than 0.7, because I'm reading only down to a particular unit. So 1 is like saying, this is what I think is at the head of the stack. Again, if you want to think about what's going to happen if you discretize at inference time, for example, the push and pop operations, then if this was pushed on with strength 0.1, with strength 1, sorry, you'd have a strength of 1 associated with the second vector, and the read would once again just be that second vector. And if it was pushed with 0, you would ignore it during the read and read through to v1. And then finally, just to illustrate removal from the stack, so at the third time step, the controller says, I want to pop with strength 0.9, so I'm pretty certain I want to remove a vector from the stack. Again, this is not proper probabilistic parlance, so I use certainty with scare quotes. So this means I'm going to remove a 0.9 of strength from the head of the stack. So 0.5 goes to 0, which means we have 0.4 left of popping energy. We remove 0.4 from 0.7 to get 0.3. And finally, we push the final vector. So now this vector here is logically removed from the stack. When we read the head of the stack, we're going to read 0.9 of v3. So that's going to dominate the return on my read. And then we're going to ignore v2 because of the strength of 0. And v1, you're going to read 0.1 of it left. So here, this is almost already discrete operation simply because the controller has, for example, learned to be very certain about whether it wants to push or pop. And we're getting the read is almost the same as just reading the top of the discrete top of the stack. The push has actually completely removed this element. So again, this is a slightly perhaps overly complex way of modeling a stack. At inference time, you may want to discretize the operations if your model hasn't properly learned to push and pop with strength 0.1, which in experiments we've seen that it does for fairly trivial data transduction problems. Or you could bite the bullet and just leave it with the ability to have a sort of yes. No, so we basically bound. We have a ReLU on that operation. So you can model. These are all differentiable operations. They're piecewise differentiable because you have to put ReLUs in, but everything is kosher with regard to producing gradients with regard to the push and pop operations given reads. So we applied this to synthetic transduction tasks. So these are, again, perfectly trivial problems to solve with one line of Python. We provided large sequences of symbols from some alphabet, and the task was to read those in and then copy them. And this is where you see LSTM start to fail to generalize quite well. And you can make these sequences very, very long. It's artificial data, so we can generate as much as we want, which is nice. Similar problem, which is reversing a long sequence. Again, from an actual scientific perspective, pretty boring problem, but it's a nice test case for exploring the limitations of in the sequence-to-sequence setting and seeing how adding a stack can help with that. We tried slightly more linguistically motivated problems, so this is completely artificial language. We're just trying to simulate aspects of real language, but I won't go so far as to claim that we're going to solve machine translation with a stack-enhanced RNN just yet. We simulated a subject-verb-object to subject-object-verb reordering. So that would be, for example, translating English into Japanese. So we use inversion transduction grammars, which if you don't know what those are, don't worry, to generate a bunch of data where there was a valid latent grammatical mapping between the left sequences and the right sequences. and we wanted to see if the stack could model that sort of like tree-to-tree transduction. We also tried to see if it could model transduction with a bit of contextual shifting. So we simulated a genderless to gendered grammar task, like translating English into German, where in English we say the regardless of whether you're talking about a man or a woman or something else. And in German, I don't actually speak German, but I'm told that there's these das, die, der. Does anyone here speak German? OK, so this is simulating English to German translation, but again, is not fully translation. And we got some interesting results out of this. So for copying and reverse, alongside stacks, we could model using similar dynamics queues and double-ended queues. So for copying, using a queue solves the problem. And by solved, I mean you get 100% accuracy, even if you test on sequences that are 2 times the length of the training sequences. So it generalizes not just within the bounds of the training sequence lengths, but outside of them, something LSTMs for these tasks completely failed to do. For a reversal, stack solves the problem, and double-ended queues solve both. This should be fairly obvious why you get these poor performances here, because if you're copying with a stack, you're pushing all the data onto the stack when you're encoding, and then it comes out in the wrong order, and similarly for a queue. So it was reassuring to see that you had bad results here because it just backs off to ignoring the stack and using the controller as an LSTM. And for the SVO to SOV problems, which there was much less diversity in the boundaries, we could get LSTMs to converge after a long time. But for most of these, the stack queue and deck, or at least the queue and the double-ended queue, which is one where you can push and pop on both ends, we could solve them. And bringing us back to this idea about rural parsimony affecting how tractable your learning problem is, this is particularly well illustrated when you look at the training and, in fact, even the validation set curves for these models. So this is, and you see this across all these experiments. So for example, in the gender conjugation thing, these 2 things that rocket to the top are the queue and the double-ended queue. And by exploiting the memory, within a few epochs, they shoot up to 100% accuracy because they're learning something similar to just 2 or 3 rules that are required to solve the problem. It's a fairly artificial problem. LSTMs and the stack, which for some reason isn't particularly well matched to this particular problem, take a long time to start vaguely approximating with like 98, 99% accuracy the training distribution, and then fail to generalize when we make it longer. So again, this is not a proof, but I think it's a strong sort of empirical nudge towards the fact that if you enhance an RNN with a data structure which allows it to take a step up in the computational hierarchy, even if your problem is regular, which these problems were in that we always had a boundary on the training data and on the test data, they're able to learn accurate solutions and general solutions much faster because they're learning they're internalizing a small set of rules rather than having to approximate a very large set of rules. Just like I said, there are different ways to produce a stack. So there's the paper, the model I talked about right here is from our NEPS paper in 2015. There's another very interesting paper by Armand Julin and Thomas Mikolov in 2015 where they simulated stacks and lists, which I think was kind of like double-ended queues. The stack semantics are similar, but a bit more lightweight in that they don't factorize the strength of the values and the actual values like we did, but have those both contiguous in that when you're pushing, you have an array of vectors and you shift those up by the value of your push, so you're interleaving your state. And likewise, popping is you shift down, or the other way around, which at training time is fine because it allows everything to be continuous, and at test time is problematic in that if you push with certainty 0.5 and then pop with certainty 0.5, every vector becomes an average of the value before and after. So push and pop are destructive unless you do them with close to perfect certainty, which is why at inference time, they discretize those decisions and you only use the continuous nature of push and pop to train the model. And that's actually perfectly valid in my mind. It's a perfectly valid thing to do. In our experiments, we didn't need to discretize, but they were very synthetic experiments. I suspect if we wanted to train a continuous stack of the form I presented on more complex problems, we might also want to discretize discretize and only exploit the continuous nature of the stack during training. But that's completely fine. There's also, and worth mentioning, it doesn't quite fit this controller memory framework I talked about earlier, but there's a really nice idea of using a pointer over previous states of an LSTM to simulate a stack in this paper by Chris Dyer and al. In 2015. It's really worth reading because there's a very cool experiment of applying this to learn shift-reduce parsing. And likewise, the experiments in Jula and Mikolov I thought were quite sophisticated compared to the ones I presented, the very artificial ones I presented. So read these papers. But just to summarize quickly what we've talked about with neural pushdown automata, these are decent approximations of classical pushdown automata. So I think that I think it would be brave to claim that these various stack-based mechanisms I just referred to take us completely from a finite state land to a pushdown automata, but it's I think, a convincing step towards this. Yes?
So before you were arguing that a standard LSTM couldn't learn to generalize beyond the sequences it saw. But in your stack model, your controller is an LSTM, right? So if it's only learned to see examples where it needs to push n times, how can it learn to generalize to 2 times n?
So you don't need to, the rule you need to learn is much simpler. You don't need to count. If you're
pushing and popping more than n times.
Yeah, okay, so count, so you're arguing that it's still going to be a problem for so for copying and for reversal, it's trivial in that it just needs to learn that, okay, I'm either in this mode, which is pushing mode, or I'm in popping mode. So I'm in my encoder or my decoder. And it basically pushes until it sees an end of sequence symbol, and then pops until it's generated an end of sequence symbol. You're correct that if it needed to track the stack depth within the controller, rather than having that be modeled by a register or something like that, that the model would probably not generalize as well beyond links where it's already learned to count. So that's a valid counter-argument to the thesis that this is directly taking us up a class in the computational hierarchy. But I think there's definitely more potential to generalize in the way that we want by being.
Definitely learn simpler rules, but your bottleneck still lies in that.
Yeah.
By your argument.
Okay. Yes. But so. Yeah, I mean, just to bring us back to my point about it doesn't matter if we're still modeling regular languages. If there's just fewer rules to learn, even if it's not going to unboundedly generalize, I still think there's evidence that, at least for these simple transduction problems, it's learning a solution in a much quicker, much different way than what the LSTMs are doing. And it's a bit of a sleight of hand to say, look, it's learning this rather than this. It might not be learning the general case of this, but it's obviously bringing something to the table. Yes, Yashra?
My question is about the fact that we're forcing ourselves into differentiable approximations of these data structures. Are we losing something when you do that in terms of expressive power or something else? Where do you see, is this a hurting or it's not a big deal?
Well, I don't think it's a big deal, but the experiments we've done are trivial. And as I'm pointing out here, yeah, I think there's been little work on applying these architectures. So aside from, and that's partly because I've done other stuff personally, and I'm sure Armo has.
I guess my question was, do you have an intuition of what could go wrong because of these sort of smooth stack operation or DQ operation?
Okay, so I mean, it's like, when you pick what data structure you're using, you're imposing an architectural bias that isn't there in the case of an LSTM. So if you pick the wrong data structure, then you're gonna suffer. You can obviously hook up a controller to several data structures. That makes the learning problem more confusing, and you lose some of maybe the elegance of modeling a push-down automata directly. So I feel like we're introducing bias at the architectural level in a way that might be harmful. But I'll be honest, I haven't actually experimented with these beyond this initial paper enough to form a strong intuition about whether this will come and bite us. And that's the exciting part of research, is we need to get around to doing that. Yes? Yeah, sorry. You don't get any signal. That's an interesting question, and let me answer that. So how do you penalize against popping when there's nothing in it? So in fact, there is a degenerate sort of training case. If your model is initialized such that the controller aggressively pops early in training, so that it's constantly removing stuff from the stack, it's never going to get a lot of gradient on that pop operation, shifting it away from popping aggressively, which is bad. So when we started training these models, I don't know if Armand and Thomas found similar problems. We found that it's like sometimes if you initialize them randomly, you got lucky and it took that beautiful behavior of going straight to 1, and sometimes it sucked. And this is really a case against automatic differentiation. So what happened is for the paper, I had written the backward dynamics of the stack in the appendix. And I looked back upon it and I thought, okay, why isn't it not learning to pop less? Why is it not learning to use the stack? And it's fairly obvious from looking at the gradient equations that it's like, okay, it's gonna reach this like degenerate state where it's never gonna get signal. So that led us to formulate an initialization strategy for the stack, which is described in the appendix, which is you simply initialize the bias on popping to -1, and then that's learned away. So that in the early stages of training, the controller is discouraged from ignoring the stack, or in another way of putting it, is encouraged to push stuff onto the stack, even if it's the wrong decision. Because if it pushes stuff on, if it learns to manipulate this tool it's given wrong, then it moves away from that behavior. If it was biased against using it in the first place, then it will never explore its capabilities. So there's a nice sort of story there. I don't know if that answers your question, but I've shoehorned something I wanted to say into it, so that works for me. OK, so let me very quickly finish. I got 5 minutes left. And I'm going to talk about register machines, so I don't want to limit. And this is neural Turing machines and similar architectures, which I love the work. I'm not a huge fan of the name. So I like to just think of these as registers. And this is the random access memory to attention's read-only memory. And arguably, if you drink the Kool-Aid, we're talking about being here in the computational hierarchy. But I'm not going to endorse that claim. I'll leave it to you to think about whether or not we're anywhere near that. So the structure here is, compare this to attention, where at each time step, the memory would, based on a key, on a query vector produced by the controller either at the previous time step or at the current time step, the memory would return a vector. In register-based memories, you're going to still have that, so you're going to read the memory in a manner possibly similar to attention or to a variant on attention. But at each time step, the controller is also going to update the memory. So the memory is now dependent on the time step. The generic sort of setup of this is that the controller, as with attention-augmented recurrent neural networks, deals with the input-output from the environment, from the text. The controller also produces distributions over memory registers for the purpose of reading from it, attention, and writing to it. The controller decides what to write and possibly how much to erase. And finally, the controller and memory states are updated using the write operation and the read operation, and as well as the input from the environment, which allows the recurrent cell to produce the output in the next state. So some unspecified but numerous equations to describe this. Our previous state is going to be the previous state of the controller, the previous state of the memory, which is now time dependent, and the previous read from the memory, although you could obviously do a late fusion kind of thing as well. Your inputs to the controller are going to be the concatenation of the inputs to the overall recurrent cell and the read. And again, this is just one of many ways to do this. The controller, based on this and its previous state, outputs a bunch of stuff. So the overall output to the network, a vector for the purpose of producing a distribution of the memory for the purpose of reading, one for writing. We call these keys typically, value, and a hidden layer. It's updated internal state. And the value is what's going to be written. The read is just going to be some read operation, for example, attention. The write is going to be, for example, you could either have an erase operation. The simplest kind of write I can imagine is you use the attention from the write key to gate between a previous value of the memory and the vector that you want to write to the memory. And A is a softmax over the positions. But there are many ways to do this, and I'm assuming that Sumit talked about the NTM in a bit more detail during his talk, so I won't bore you with the finer details. But there are a lot of extensions you can put into this idea. We can explore location-based addressing, where the state is now containing something that we don't actually care about, the differentiability of it, like a one-hot vector over positions in the memory. And the controller simply emits a differentiable shift operation, for example, circular convolution, that allows you to update the position that the read head is happening at each time step. You can mix location and content-based addressing. You could explore hard addressing using reinforce. I believe Cho and Joshua have a paper on this one, and other people here. So I'm in the presence of geniuses. This is great. And then there are more esoteric heuristic addressing mechanisms, but ideally you want to keep those differentiable. And I leave you to read those in the literature and upcoming literature. Other things that can be looked into are factorizing the key and content factorizing the key addressing mechanism in the memory and the is this something you guys did in your paper too? You did, oh yeah. So if you think about the memory being empty and you want to write, right, and the write key is a vector and you're doing a content-based lookup on an empty memory, everything is 0. So by definition there, the attention is simply going to return a uniform distribution over all the values in the matrix. And at that point, you're just distributing your vector over the entire contents of the matrix, and that doesn't sound very sensible. So one thing you can do is reserve part of your memory matrix for either a fixed or learnable prefix schema that you initialize with orthogonality constraints so that each position, even when the memory is empty, has some sort of value that's going to be used for the key in order to be able to select a position. And there's plenty of cool things you can do in this space. The relation to actual Turing machines is there, but perhaps a little tenuous. So here, as Joshua pointed out earlier, you can think about the RNN cell as internalizing the tape. This is definitely the paradigm being espoused here, where part of the tape, at least, is internalized in the form of the addressable register-based memory, and part of it's still outside in the symbols you're reading from, so it's a little weird. The controller can control the tape motion via various mechanisms like content-based addressing or shifting an index. And the RNN could therefore learn to simply focus on modeling the state transitions. But there's still a weird split between the external and internal internal tape in the sequence-to-sequence paradigm that I don't quite like. So I'm not super convinced that this is going to be modeling a Turing machine. The most crucial reason why is in the number of computational steps in the standard sequence modeling for a neural Turing machine, for example, is tied to the data. So imagine you're trying to sort with, has anyone read the neural Turing machines paper where they show that it could learn to sort sequences? That blew my mind because it's learning a problem that I thought was O(n) log n and O(n) time. And so I thought, okay, that's impossible. What actually it's probably doing is approximating something like radix sort, which is O(n) and then has particular bounds on the data it can sort. If you wanted to learn quick sort with a neural Turing, you'd have a bit of a problem in the sequence-to-sequence setting because the neural Turing machine would need to read in the input symbols and then choose how much time to start rearranging things internally before it started outputting the sorted sequence. And currently, unless you explore a latent variable modeling approach to pondering, there's no easy way to do that. So I think there's a bunch of limitations that prevent you from modeling an actual Turing machine. And this applies to the stacks as well. So you can imagine a controller with 2 stacks being capable of doing the copy problem quite well, in that the encoder would push everything to one stack, then you'd have n steps where the controller swaps data from one stack to the other, and then you pop everything out, and it comes out in the right order. But the crucial point here is the model would need to learn that it needs to think or ponder for n steps in a data-dependent way in order to be able to shift the data around in dimensional representations. And there's no elegant way to do this in our standard maximum likelihood-based training. And I need to quickly wrap up. So I think it's still unlikely to learn a general algorithm, but the experiments show that there is better generalization on symbolic tasks. So is it reaching the level of Turing machines? Probably not, but we're getting some computational benefit out of it. And I can summarize this slide as saying there haven't been many applications of this to natural language understanding, but there's fascinating research to be done here. So this is kind of the peak of research. So I'd like to quickly conclude this talk with some sort of general recommendations. We've seen various intuitions about examining the limitations and capabilities of different kinds of models around the theme of recurrent cells. It's easy to design an overly complex model, and it feels very nice and powerful. I'm gonna write the next crazy model that's going to replace an LSTM. It's rarely worth it unless you actually spend time trying to understand the limits of your current architectures within the context of the problem you're studying. And that's probably one of the most informative ways of developing new models. By looking at existing architectures, understanding the limitations and their nature, often better solutions and extensions just pop out of this. And the best example of this, for me, is chapters 1 through 3 of Felix Gur's thesis on LSTMs. And I read this. It starts with an analysis of the vanishing gradient problem and the exploding gradient problem for RNNs. And then he just very clearly shows how an obvious solution is the gating mechanism. And it's a very obvious idea. Once you see it written like that. And I thought that was really beautiful. And I'm sure there are many papers by people in Montreal who also have that property. By the way, because there are a lot of grad students here, and you're typically grumpy when you're reviewing, when you see a paper and the idea seems really obvious, that's usually the mark that it's a good idea. That doesn't mean it's a trivial extension to something. So remember that when you're reviewing our papers for NIPS. Yeah, so think not just about the model, but think about the complexity of the problem you want to solve and whether the model you're using, say a simple RNN, is going to be appropriate for that level of complexity. And then finally, just not to be too grumpy about examining complex models. Don't be afraid to be creative. There are plenty of problems to solve in natural language understanding and in other domains that will require creative new models rather than the models we currently have. So don't just exploit, but explore. Thank you very much.